Welcome back, my dear friends. So, we have seen what complex variables are, we have defined functions, we have come to analytic functions, harmonic functions. Now, you know how to find an analytic function if the real or imaginary part is given. You know what are orthogonal trajectories, what is its significance in the analytic function, etc., etc. When we have started with the complex functions, we have seen that your functions can be represented as mappings. But here your function f of z is equal to u plus iv, where u and v are functions of real variables x and y. So, in order to represent w is equal to f of z, you need two parallel planes. You identified one plane as z plane and the other plane where you map the image of w is equal to f of z as the w plane. The complex function w is equal to f of z, which you write as u of x y plus I v of x y, can be also considered as a planar transformation. That means, you can represent it in a plane. We also call w is equal to f of z as the image of z under f. So, in this figure, as I have told you, we need to have two parallel planes. One of the plane you identify as the z plane and the second one as the w plane, where in your z plane you mark your x and y axis as the real and imaginary axis, whereas in the w plane you have the corresponding u and v as the real and imaginary axis. So, under the function w is equal to f of z, each point, say you have 3 points z1, z2, z3 in the z plane and their images which are plotted in the w plane, w1, w2, w3. So, z1 goes to w1, z2 goes to w2 and z3 goes to w3. Now, let us start with a simple example. We will consider a function f of z is equal to e raised to z. If z is equal to a plus it, where 0 less than or equal to t less than or equal to pi, that is t is varying from 0 to pi, and w is equal to f of z, you can write as e raised to a into e raised to it, because your z is a plus it. Thus, this is a semicircle with center w is equal to 0 and radius r is equal to e raised to a. If z is equal to t plus ib, where t varies from minus infinity to infinity, then w is equal to f of z, which is e raised to t into e raised to ib. Thus, this is a ray with argument of w as b and modulus of w as e raised to t. So, this is shown in the next figure. So, here you can see how the image is. So, here e raised to a into e raised to it, if z is equal to a plus it, is a semicircle with center w is equal to 0 and radius r equal to e raised to a, which can be seen in the figure b. So, you are having your z plane here and the corresponding w plane, and you can see that argument w is equal to 0 coincides with your u axis and w is equal to pi with the negative u axis. Now, the complex function f is equal to 1 by z has domain z not equal to 0, and what is the real part of f is equal to 1 by z? Here you will have to rationalize the denominator. So, you get u of x y as x by x square plus y square and the imaginary part v of x y as minus y by x square plus y square. If a is not equal to 0, u of x y is equal to a can be written as x square minus 1 by a x plus y square, which is nothing but a circle with center 1 by 2a comma 0 and radius 1 by 2a. So, what is happening to u is equal to a constant? U equal to constant becomes, it is nothing but the circle with center 1 by 2a comma 0 and radius 1 by 2a. In the same way, v of x y is equal to b. For b not equal to 0 can be written as x square plus y plus 1 by 2b the whole square is equal to 1 by 2b the whole square, which is nothing but a circle with center 0, minus 1 by 2b and radius 1 by 2b. So, this can be seen in the figure. So, your circles which are having radius 1 by 2a, 0 and radius 1 by 2a, and similar circles with radius 0, minus 1 by 2a and radius 1 by 2a. So, let us see some of the basic transformations. The first one is translation. The function f of z is equal to z plus z naught is interpreted as translation, and the basic transformation rotation is given by g of z is equal to e raised to I theta naught into z, or else I can write it as gz is equal to some constant c into z, where c is a complex number. So, z plus z naught gives you translation and gz is equal to c into z gives you rotation. So, if you have to find a complex function that maps minus 1 less than or equal to y less than or equal to 1, that is a strip, to 2 less than or equal to x less than or equal to 4. See, from the figure we can see that minus 1 less than or equal to y less than or equal to 1 is first rotated through 90 degree and then shifted 3 units to the right. So, the mapping can be written as h of z is equal to e raised to I pi by 2 into z plus 3. So, it is shifted by 3 units and it is rotated through 90 degree. So, that is nothing but I into z plus 3, where e raised to I pi by 2 is nothing, your imaginary constant I. See, if you see the figure, you can easily identify that your strip minus 1 less than or equal to y less than or equal to 1 is actually rotated through 90 degree and then shifted by 3 units towards the right. So, another basic transformation is magnification, which is given by the function f of z is equal to some alpha z, where alpha is a fixed positive real number. So, we have seen that rotation is also given by something like f z is equal to some c into z, but there the case was your c is a complex number. So, if your c reduces to a positive real number, then it becomes magnification. So, the modulus of this function w is mod of alpha into z, that is alpha times mod z. So, if gz is equal to az plus b and a is some r naught e raised to I theta naught, I am using the exponential form, then the vector is rotated through theta naught magnified by a factor r naught and then translated using b. So, if this is an example where we have combined all the 3 basic transformation, the translation, rotation and magnification. So, coming back, f of z is equal to z plus z naught, where z naught is a complex number, will give you translation. So, f of z is equal to a constant into z, where the constant is a complex constant, that is a complex number, will give you rotation, and depending on the modulus value, it will be magnified. So, if your constant reduces to a real number, then magnification only happens, there is no rotation. So, in general, if I have a transformation gz is equal to az plus b, then you have magnification, rotation and translation happening together. So, if again suppose if we have to find a function that maps the disk mod z less than or equal to 1, and you know that it is your standard unit circle and the set of all interior points, which you denote as mod z is less than or equal to 1. So, you need to find out which function will give you the image as the disk w minus 1 plus I less than or equal to half. That means, it is a circle with center 1, 1 and radius half and set of all interior points inside it. So, actually what is happening? It is magnified by half, or else if we say contracted by half, and it is translated to 1 plus I. The earlier center for the circular disk mod z less than or equal to 1 is 0, 0 and the radius is 1. Now, the radius is reduced to half whereas the center is shifted to the point 1 comma 1. So, if I want to find a transformation W is equal to f of z in the form az plus b, what will I be having? So, here modulus of A will give you the magnification. So, here in this case negative magnification is happening, which is your contraction. So, W is equal to half times Z plus the shift that has happened is 1 plus I. 0 0 is now shifted to 1 comma 1. So, now let us see the power function. Say for example, f of z is equal to z raised to alpha, where alpha is a fixed positive number. Such a function is known as a real power function. So, here in this your z is having a real positive number as the power. So, you call it a real power function. So, in the figure, if z is equal to r e raised to I theta, so we are using the exponential form here. So, it becomes easy for you to find the image. So, z raised to alpha becomes f of z is equal to r e raised to I theta the whole raised to alpha, which will reduce to r raised to alpha into e raised to I alpha theta. So, what is actually happening? So, you can see that the original length or distance from the origin, which is r, and the angle it has moved from the positive x axis theta, that is your z, is equal to r comma theta or r e raised to I theta. The image of this function or this point under the function w is equal to f of z, which is z raised to alpha, is r raised to alpha comma alpha theta. So, your distance from the origin has become r raised to alpha now, and the angle theta has become alpha times theta. So, it is clearly given in the image. Your original point is z is equal to r e raised to I theta, and its image under w is equal to f of z, which is r raised to alpha e raised to I alpha theta. Okay, now let us find a complex function that maps the upper half plane y greater than or equal to 0 onto the wedge 0 less than or equal to argument of w less than or equal to pi by 4. See, the upper half plane can also be described as 0 less than or equal to argument of w less than or equal to pi. So, thus f of z is equal to z raised to 1 by 4 will map the upper half plane onto the wedge 0 less than or equal to argument of z less than or equal to pi by 4, because here you are trying to find out a function actually mapping your argument of z from 0 to pi to argument of w from 0 to pi by 4, which will be obtained by f of z is equal to z raised to 1 by 4. So, in the same way you can have successive mappings also. You have seen that your complex mappings can be, or else the complex functions can be expressed as mappings, and suppose I have function of a function. Say if zeta is f of z, it maps r to r double dash, and w is g of zeta. It is a function of the function zeta or g of f of z. In this case, it maps r double dash to r dash. So, w is equal to g of f of z maps r onto r dash. So, you have now 3 parallel planes. One will be your z plane, and the second will be your zeta plane, and the third will be your w plane. So, since w is equal to f of gz, f maps your z plane onto zeta plane, and from zeta plane through g, the function g, you go to w plane. So, in effect what is happening, your function f of g of z is mapping z plane onto w plane. So, this is how mapping happens when it is successive. In the previous examples, we have seen that f of z is equal to e raised to z maps 0 less than or equal to y less than or equal to pi onto 0 less than or equal to argument of zeta less than or equal to pi, and g of zeta is equal to zeta raised to 1 by 4 maps 0 less than or equal to argument of zeta less than or equal to pi onto 0 less than or equal to argument of w less than or equal to pi by 4. So, actually your strip 0 to pi is mapped onto the wedge 0 to pi. So, from z plane you are moving to zeta plane by the function f, and as in the previous example, the wedge 0 to pi is mapped to the wedge 0 to pi by 4 under the mapping g of zeta is equal to zeta raised to 1 by 4. So, in effect, if you have the mapping w is equal to g of f of z, you need to define it as g of e raised to z, and that is nothing but e raised to z by 4. So, if you have to express it as the successive mapping from the z plane onto the w plane going through zeta plane, the complex function w is equal to e raised to z by 4 will map your strip 0 to pi onto the wedge 0 to pi by 4 in the w plane. Suppose we have to find a complex function that maps argument of z between pi by 4 and 3 pi by 4 onto the upper half plane v greater than or equal to 0. So, again the mapping is from z to w plane. So, if we have to consider it as a function of a function, first we will rotate pi by 4 less than or equal to argument of z less than or equal to 3 pi by 4 by zeta is equal to f of z, which is e raised to I pi by 4 into z. So, then we magnify it by 2, that is w is equal to g of zeta is zeta square. Thus, the desired mapping is w is equal to g of f of z, that is e raised to minus I pi by 4 z the whole square, that is nothing but minus I into z square. So, if we have to consider it as a successive mappings from z plane to the w plane through the zeta plane, your function is nothing but w is equal to g of f of z, that is minus I z square, which will map the wedge pi by 4 to 3 pi by 4 in the z plane onto the upper half plane v greater than or equal to 0 in the w plane. So, now moving on to conformal mappings. We have just seen that how your function will be represented as mappings, and if you just see the maps, the given region and its image, how do you find out the complex function? And those are done just by using the basic transformations. Conformal mappings are nothing but angle preserving mappings. A complex mapping w is equal to f of z defined on a domain D is called conformal at z equal to z naught in the region D when f preserves that angle between the two curves in D that intersect at z naught. See, I have a z plane where I have say two curves C1 and C2, and the angle between those are the angle theta. Suppose I have a function w is equal to f of z that maps the curve C1 onto C1 dash and C2 onto C2 dash, still the angle remains the same. So, your theta has to coincide with phi, then I say the mapping is conformal. When I say the mapping is conformal or theta is the same or the angle is preserved, the angle has to be preserved both in magnitude and direction. If it is only preserved in magnitude, you say the mapping is isogonal. So, conformal requires a little bit more, it needs the angle to be preserved both in magnitude and direction. You please refer the figure, then modulus of z1 dash minus z2 dash the whole square is equal to mod z1 dash square plus mod z2 dash square minus 2 times mod z1 dash into mod z2 dash cos theta, or the angle theta is cos inverse of z1 dash square plus mod z2 dash square minus modulus of z1 dash minus z2 dash the square, the whole divided by 2 times mod z1 dash into mod z2 dash. In the same way, its image C1 dash and C2 dash, the correspondingly W1 dash and W2 dash, if we have to find the angle phi between the curves C1 dash and C2 dash, we get phi as cos inverse of W1 dash square plus mod W2 dash square minus modulus of W1 dash minus W2 dash square, the whole divided by 2 times mod W1 dash into mod W2 dash. This is the angle, this is how you find the angle in terms of your Z1 and Z2. So, if these two angles remains the same, then we call it conformal mapping. So, again, how is it having some relation to your analytic function? So, let us see this theorem statement which says if your function f of z is analytic in the domain D and f dash z is not equal to 0 at a point z naught, then f is conformal at z equal to z naught. So, let us quickly see how this is true. If a curve C in D is defined by z is equal to some z of t, then w is equal to f of z of t is the image curve in the w plane. So, we have w is equal to f of z of t and w dash is equal to f dash of z of t into z dash t. Suppose we have two curves C1 and C2 intersecting at a point z equal to z naught, then w1 dash is equal to f dash of z naught into z1 dash and w2 dash is equal to f dash of z naught into z2 dash. Since f dash of z naught is not equal to 0, we can use the definition to find angle, that is phi is equal to cos inverse of, if we substitute for w1 dash and w2 dash in the previous formula, we get phi as cos inverse of f dash of z naught into z1 dash square plus mod of f dash z naught z2 dash square minus modulus of f dash z naught z1 dash minus f dash z naught into z2 dash square, the whole divided by 2 f dash of z naught into z1 dash mod f dash z naught z2 dash. This is nothing but we have just substituted your w1 dash and w2 dash, what you have obtained in the function or else in the expression to find the angle. So, this reduces to cos inverse of mod z1 dash square plus mod z2 dash square minus modulus of z1 dash minus z2 dash square, the whole divided by 2 mod z1 dash into mod z2 dash, which is nothing but your theta. So, what is theta? Theta is the angle between the curve C1 and C2, and here phi is the angle between the curves C1 dash and C2 dash, which are the images of C1 and C2 under W is equal to f of z. So, what can you say about the analytic function f of z is equal to e raised to z? Is it conformal? See, as per the theorem, your function f of z, if it is analytic and f dash z is not equal to 0, then it has to be conformal at all the points. So, what can you say about f of z is equal to e raised to z? What is its derivative? Its derivative is f dash z, it is again e raised to z and which never becomes 0. And you know that f of z is an analytic function and its derivative never becoming 0. What does it say? According to the theorem, your function f of z is equal to e raised to z has to be conformal at all the points in the z plane. Now, suppose gz is equal to z square. What can you say about that function? Still it is an analytic function and its derivative is nothing but 2z, but it becomes 0 when z equal to 0. So, your function gz is equal to z square will be considered as a conformal mapping, but at all points except z equal to 0, because g dash z becomes 0 at z equal to 0. Now, consider the vertical strip minus pi by 2 less than or equal to x less than or equal to pi by 2, which we call as the fundamental region of the trigonometric function w is equal to sin z. A vertical line x is equal to a in the interior of the region can be described by z is equal to a plus it, where t varies from minus infinity to plus infinity. See, if I expand your sin z as sin of x plus iy, it is nothing but sin x cos hy plus I cos x sin hy. Also u plus iv is equal to sin of a plus it, that is sin a cos ht plus I cos a sin ht. And since you know that cos h square t minus sin h square t is equal to 1, becomes u square by sin square a minus v square by cos square a is equal to 1. So, the image of the vertical line x is equal to a is a hyperbola with plus or minus sin a as u intercepts, and since minus pi by 2 less than a less than pi by 2, the hyperbola crosses the u axis between u is equal to minus 1 and u equal to 1. Note that if a is equal to minus pi by 2, then w is equal to minus cos ht. The line x is equal to minus pi by 2 is mapped onto the interval minus infinity closed minus 1. Likewise, the line x is equal to pi by 2 is mapped onto the interval 1 comma infinity. So, let us conclude what all things we have learned in this session. As we have discussed in the beginning of complex variables, we just saw how a complex function is also treated as a mapping. We have seen some examples in which by seeing the images you were able to identify the function which maps the given region onto the image point. And also we have seen what is conformal mapping and how is your analytic function related to conformal mapping. Thank you for watching. We will continue with this topic in the next session.